Hello everyone, welcome to our physics experiment video presented by our group members, which are Luis Gabriel Cianata from 11.3 as the scriptwriter and video editor, Ana Sofia Lizucardi from 11.3 as the scriptwriter and video editor, and finally your presenter, me, Miyamata Irishbel Clariza Arifin from 11.4. So, have you guys ever been on a roller coaster and felt the exciting rush as it loops and twists, defying gravity with every turn? Well, have you ever wondered what keeps you safely on track, even when you're upside down? That's where centripetal force steps in. In this video, we're diving into the science behind those thrilling twists and turns through a simple centripetal force experimentation. Without further ado, let's begin. So in this experiment, our goal or our objective is to find the value of gravity on Earth. Now, you may wonder, how are we going to do that? So, we're going to explain by theory first. For this experiment, the centripetal force is acting upon the object for the circular motion created. According to Newton's first law of motion, objects will remain in uniform motion in a straight path unless there's external forces acting on it. Whereas the second law of motion indicates unbalanced forces that is required to change the motion of an object. In this case, there's a continuous unbalanced force acting on the object to keep moving in a circular motion. And this is what we call the centripetal force itself. Now, how do we calculate the magnitude of the centripetal force? Well, the magnitude of the centripetal force depends on the object's mass as well as the object's acceleration. The acceleration of an object moving in a circular motion is defined by A equals to v squared divided by r, where v is the velocity and r is the radius of the circular path of the object. Hence, force can also be calculated by F equals mv squared divided by r. Velocity itself can be defined by distance divided by time. To find velocity in a circular motion, velocity can be calculated as v equals 2pr divided by t, which 2pr is the distance of one circle and t, or period, is the time it takes for one revolution. Based on this, we can calculate the formula for force, which is F equals 4p squared rm divided by t squared. So for this experiment, the apparatus and materials needed are first a stopper, second a glass tube with a small diameter, third a marker, fourth a ruler, fifth a washer, and sixth a string, and finally a stopwatch. Now for the procedure of the experimentation. To begin this experiment, a string is inserted to a glass tube with one end tied to the stopper and the other end of the string attached to the weights whose mass will be our control variable. Instead of the adhesive tape, you can simply opt for a marker to mark the different radii on the string. Now let's take a look at a video demonstration. Firstly, hold the glass tube, making sure the string remains untouched, and carefully swing the stopper in a circular motion. Start the stopwatch until the mark is just under the glass tube.
Start counting the rotations. Once 20 rotations have been completed, stop the stopwatch and record the time taken. Repeat this process with different radii.
Now from this experiment, as the stopper moves in a circular path, there are two distinct forces, the outer momentum pushing against the inward tension exerted by the string. Furthermore, the stopper's velocity contributes an additional force perpendicular to a circular trajectory, reinforcing the inward tension. Now these two forces act in unison, sustaining the ball's circular motion. We experiment with different radii, our independent variable, which directly influences the period, which is the time required for a single rotation, which serves as our dependent variable. To calculate the period, we simply divide the time taken in seconds by the number of rotations. Our control variable in this experiment are the mass of the loads and the mass of the stopper, in which the mass of the load is 179.4 grams and the mass of the stopper is 44.1 gram. After obtaining all the data that we need, we process the data and put it into a single table, taking note of the radius of circle of motion, the time taken for 20 rotations, the period, and also the period squared. As you can see, the table that we obtained is as given. This data is then graphically represented using a scatter diagram in which the independent variable is plotted in the x-axis, which is the radius of the circle, whereas the y-axis, which is the dependent variable, which is the period squared. The graph should demonstrate a positive correlation, illustrating that as the radius increases, the period should increase along with it. The best fit line shown on the graph shows the gradient, which is the change in y-axis divided by the change in x-axis. The gradient of the best fit line is 1.127, which is equal to the change in period squared divided by the change in radius of circle of rotation. In order to find the gravitational acceleration, we can use the formula Fc, which means centripetal force, which is equal to Fg, the gravitational force. Now, centripetal force is expressed as mass multiplied by velocity squared divided by the distance, represented by r. As mentioned before in our basic theory, the formula can be further derived by substituting the velocity to Fc, which is equals to 4p squared times r times the mass of the stopper divided by the period squared. According to Newton's second law, which is F equals to m times a, gravitational force is equal to the mass of the waves multiplied by the acceleration due to gravity, which is around 9.81 meters per second squared. You can therefore find the value of gravitational acceleration using the formula T1 equals 4p squared times r times mass of the stopper divided by the period squared, and T2 is equals to the mass of the weights times gravity, which we get T1 is equals to T2. After that, we can substitute the formula, which is equals to 4p squared times r times mass of the stopper divided by T squared, or period squared, is equals to the mass of the weights times gravity. As the gradient of the best fit line equals to the period squared divided by the radius of the circle, we can input this value into the formula if we inverse the gradient itself. And hence we can make the formula into G is equals to 4p squared times the mass of the stopper divided by the mass of the weights and times the gradient. The gravitational acceleration can then be calculated by inputting the values into the equation, which we will get around 8.61 meter per second squared. Don't forget to convert the mass of the stopper and the weights from grams to kilograms so that you don't get any weird values. After collecting all the data and processing the data into graphs and tables, we're going to start into the analysis. So first, we're going to start with a percentage error analysis. Now first, the error value can be calculated using the formula. Error value is equals to EV minus AV divided by AV times 100%. Now the EV is the 8.61 that we have calculated from our experiment, and the AV is 9.81, which is the actual value of gravity. After inputting these values into the equation, we're going to obtain a value of 12.2%. As we can see here, the percentage error exceeds 10%, which means the result could actually have been more accurate. Now, there are actually several factors that could have contributed to the observed errors in the centripetal force experiment. First and foremost, the irregular motions such as fluctuations or wobbling in the stopper's trajectory could have influenced the data. It's extremely important to ensure the consistent and stable motion before starting the stopwatch to optimize the experiment's reliability. Additionally, external influences such as air resistance or friction between the strings and the edge of the glass tube might have disrupted the smoothness of the circular motion. Furthermore, inaccuracies in the measurement process such as imprecise timing or inconsistent counting of rotations could have affected the final result. Now, the solution to these errors is that we could do the experiment in a controlled environment with minimal external disturbances. That precise measurement is done by providing repetition and that the circular motion is stable. By adhering to these steps, we can minimize the error margins and gain more reliable outcomes in our future experiments. To conclude our experiment, we have obtained gravitational value, which is 8.61 meters per second squared based on our experiment. So that is it for our video, and we hope you enjoyed this video. Thank you for everyone for watching.